All right, ladies and gentlemen, you asked for more worked out problems, and that's what we're working on today. So these are a couple more isotope practice problems, and it says industry applications here. This is actually the first page of 3. The industry applications are on another page. So we'll get to those today, but not right now. The first problem here is a review question. If you have trouble with this, turn back to 154. The rest of these problems are extensions, sort of new ideas, new things you can do based on our homework on 159. So if you haven't finished our homework on 159, or if you didn't understand it, you should turn back and work on this one. I've got another video on that. So we can do these problems with 3 isotopes, and we can do them with some unknown values. And that's what this set of practice problems is about. It's about unknown values. You saw a couple of those on 159, but we're going to flesh that out a little bit. So I made this table to help keep track of what we do and don't know about these 3 isotopes. So our question says, consider an element that has 3 naturally occurring isotopes. The isotopic masses and percent abundances are, and then it gives you the mass number and the abundance for the first 2, but only the mass number for the last one. Then it asks, what is the average atomic mass of the element? And then based on this, what is the element? So let's start organizing this information. Isotope number 1 is about 54 AMUs. We can assume its mass number is 54. 54 AMUs. And its isotopic abundance is 5.845%. Isotope number 2, its mass number is about, or its isotopic mass is about 56, so its mass number is probably 56. And it is 91.754% abundant. So I'm betting that the average atomic mass of this element is going to be pretty close to 56, since most of it weighs 56 AMUs. Now, for our third isotope, we do have the mass, 57 AMUs, but it doesn't give us the percent abundance. But since it only has 3 naturally occurring isotopes, we know that these 3 numbers should add up to 100%, because that would make up 100% of the isotopes we're seeing in nature. So we can do this math pretty easily. We're going to do 100% minus 91.754 minus 5.845. When we do that, we get 2.40% abundance. All right, now this next box is A average. That is the average mass. And it gives you an equation for this. It's a little bit confusing looking, but it's just the mass number times the abundance, plus the mass number times the abundance, plus the mass number times the abundance. So let's write this out down here. Okay, it's going to be 54 times the abundance. Remember, we can't write the abundance in a percent. We can write this over 100, or we can convert it to a decimal form, which would be 0.05845 plus 56 times 0.9174 plus 57 times 0.0240. I got those decimals just by dividing this by 100, but you can also just scoot the decimal place 2 to the left, and that'll give you these decimals. Okay, so grab your calculator, calculate those out, pause the video if you need a second. When I do the math, what I get is 55.90711. So that's going to be our average atomic mass, and the units on that will be AMUs. Okay? Although we don't always do units for this particular measurement, because it could be lots of different things. We'll talk more about that in another class. 90711. There we go. All right, based on that, what element is this? Grab your periodic tables. Let's take a look. We're looking for something with an atomic mass at about 55.9. So let's take a look here. 55.9, here's 50, 51, 54, ooh, 55.8, and the next one is 58 something. So I'm betting that this is iron because it has a pretty close average atomic mass. So that's how you complete this kind of problem, problem where we're missing something. All right, let's take a look at these other problems here. This next one is just totally straightforward, exactly the same as this one. So I'm going to give you a second to work this problem out. You can pause the video, work it out, and then I'll work it out with you when you come back. So here we go. Same thing. You don't have a table, but you do have the atomic masses, the abundances, and we're missing the percent abundance on this last one. Okay, so let's write this out. And you'll notice here, it's not exactly 20 for neon 20. They're just giving you the exact atomic masses. Remember that the AMUs are an estimation. Okay, but on these sets of problems, we're working with some exact values. So it's going to be 19.992. That's what the isotope weighs. And we're going to multiply that by 0.9051. That's the percent abundance. We're going to add that to the weight that's contributed by neon 21. So that's going to be 20.993 times, ooh, this is tricky. Move the decimal place 2 to the right, or 2 to the left, excuse me, 1, 2, is going to give us a very small number. So 0.0027, make sure you keep track of those decimal places. And then for this contribution of the weight from neon 22, we know the weight, it's going to be 21.991 AMUs. And we're going to multiply it by the remaining percent. So there's a couple different ways we could do this. We could just do 100 minus 90.51 minus 0.27, and that will give us the remaining percent that's contributed by neon 22, and that would be 9.22%. But if you're doing this with a calculator that can do some parentheses, the easiest way to do it in my mind is just to do 1 minus 0.9051 minus 0.0027 and plug that in, because that will give you the remaining percent. So that's one way I like to do this. And when we calculate this out, we just plug it all in. You're going to get 20.179 AMUs. That's our average isotopic mass for this, which makes sense.